All right, next, now that we've talked about the definition of a derivative, we're going to talk about estimating them, or a bunch of different ways that we can find the rate of something. So this involves looking at the property of a derivative and what we've learned about it being a rate or a rate of change. So the derivatives describe the instantaneous rate of change of a function. And what that means is that it describes how quickly the function changes compared to the input changing. So in other words, if it's a big derivative, that means the function changes a lot for a tiny change in the input. If it's a small derivative, that means the function only changes a little for a big change in the input. And when you graph this, you get the slope. Or in other words, when you graph it, the slope can be found with the derivative. So that number that we found earlier, derivative, the number that you get for off of a function, that is the slope of the tangent line at that function, the slope or the rate of change of the function at that time. So let's look at this for a second. Let's say f of x is equal to 3x plus 2. What's the slope? The slope is 3. And so if I have f prime of x, I'm just telling you that f prime of x is 3. And that makes sense because the slope of this function is 3 everywhere. So the derivative should be 3 everywhere because it's always got a slope of 3. But this is the key thing to take note of here. You can estimate the derivative by estimating the slope off of a graph. Secondly, derivative property, in order to differentiate, a function must be smooth and continuous. So smooth means no sharp turns or corners on your graph. So if you've got something like the absolute value function, that's no good right here because that's a sharp corner. If you've got like a parabola, that's fine because there's no sharp curves. It's just a nice and smooth. So there is a technical math definition for this, but the kind of a little bit looser hand-wavy definition of it doesn't have any points or it doesn't have any corners is a lot easier for us to work with. And so if you know that, then you can just say, hey, this is smooth, and you don't have to explain why you know it's smooth. You just can say this function is smooth. It's also got to be continuous because if you've got something like this, you can't define the derivative here because the function has this jump in it. There's no, it doesn't make sense to talk about the slope here because it's not continuous. So in order to differentiate, a function must be smooth and it must be continuous. This also means that therefore a derivable function is smooth and continuous. Continuous. So this derivable, that's not a good word. We'll use the proper word, a differentiable. Differentiable. So a differentiable function is smooth and continuous. So if I tell you this function is differentiable, I've also told you it's smooth and it's continuous. And so these two things are just important to know. And really what we're looking at is that the slope of a function, or the slope of a graph will help you estimate the derivative of that function. So if the slope is, say, sharp, you don't know what the slope is at that point. So that's the derivative is undefined there. If the slope is vertical, that means technically the slope is undefined. So what is the derivative? Also undefined. So that's what we're looking at here. You can also pull this from tables using the same idea. So if you've got a table of a bunch of values, if you estimate the slope from that table, you've estimated the derivative.